Hi, my name is Yasha Hetzel, and today I'm going to share with you some of the work we've been doing to try to improve extreme sea level estimates around Australia using a coupled wave surge model. Uh, this is kind of motivated through a federally funded project we did to develop a consistent estimate of extreme sea levels around the coast of Australia using a hydrodynamic model. This resulted in a 59-year hindcast of water levels on which we calculated extreme values and made a website where the information could be accessed by the public. That's that red URL on the bottom there. Now, just to see what you get on the website, if you click anywhere, zoom in and click anywhere on the coast, you get high resolution points containing 100-year ARIs around the coast and a number of plots. So return period curves, some time series information, and also you can download the data for any points and also for the same analysis done to tide gauges around the coast. Through that work, we identified a few different challenges with modeling the extreme sea level. So the type of storm, in particular tropical to extratropical storm transition, surface wave effects, so wave setup and other effects, continental shelf wave, and meteorological tsunamis. The picture you see on the left was actually a really destructive storm on Australia's east coast near Sydney. You may have seen a picture of that, where it actually wasn't a big storm surge, but there were very large waves coming from the northeast, which caused a lot of damage and erosion at the coast. And so accounting for waves is obviously going to be particularly important in some places. The modeling system we used was a coupled modeling system called Schism, coupled with the wind wave spectral model. So Schism is a hydrodynamic model, WWM is the wave model, and the wave model gives wave-dependent wind stress and wave momentum stress. That's the wave setup component to the hydrodynamic model, and at each time step, hydrodynamics feed back in the sea level and the currents. The cartoon on the right, we just want to point out that total water levels consist of a number of processes, one of which is wave run-up at the coast. We're not looking at that. We're looking at wave setup, storm surge, and wave effects on the wind at the surface and how you parameterize that. The grid we used covered all of Australian water, so it's a very large grid with high resolution up to 100 meters at the coast and greater than 10 kilometers offshore. We were able to run it in coupled mode for all of Australia, but we also did subsets of the exact same grid to run it faster for the region. And in this case, I'm showing you work from Queensland there, which is a quarter of the grid. The bathymetry was derived from a number of sources, basically the best we could find. Using sensitivity studies and the coupled and uncoupled simulations, we looked at a number of storms, 4 of which are shown here. So 2 tropical cyclones, transitioning storm, and an extratropical low pressure system in the south. But what I'm going to present here is just one of them. So tropical cyclone Yasi. And we did not include tides in the situation where we're looking at the sensitivities. Total water levels are important, but to eliminate any confusion, we just focused on surge and the waves, but no tides. Cyclone Yasi was one of the most intense and largest tropical cyclones to cross the coast in Australia. Major damage, huge waves, and storm surge. The wind and pressure forcing for the model, we looked at using reanalysis models, and as many of you know, the reanalysis models in general underpredict the intensity of tropical cyclones. And a common way to address that issue is to use a parametric tropical cyclone vortex, such as the Holland model. We've found that using a merged version of the Holland 2010 with Japanese reanalysis, JRA 55, worked pretty well. On the right, you see 2 slices across the core of the storm, red showing the hybrid merging where we've replaced the vortex with the parametric model, and the synoptic wind fields are outside of that region. Blue is the raw JRA 55, red is the merged forcing, and you see the intensity is much stronger in the one where we've replaced the vortex. Track differences, we looked at a couple of different reanalysis as well. The ERA interim had the track more than 100 kilometers away from where the JRA 55 and the best track estimates were, so that wasn't going to be very useful for this storm. And JRA 55 has some sort of assimilation to get the track in the right place, so that worked for us. The waves we calculated were close to observation, so in the limited comparisons we had with satellites and the wave buoy offshore, the dots represent the satellite and the spatial field is the simulated waves. Doing a pretty good job, greater than 12 meters offshore, 6 meters near shore. The Great Barrier Reef really dissipated much of the wave energy, but they were still relatively large. So the dots inside the reef there show it still more than 6 meters. Townsville a little bit further to the south, out of the domain there, but 5-meter waves and matching pretty close in amplitude to our models from the observations. Looking at just a snapshot of the significant wave height, you see that near shore the effects of the Great Barrier Reef here offshore, and near the coast to complicated islands and reefs showed that really that unstructured grid was essential to reproduce the waves accurately. Storm surge and Cardwell here, where that red star is, that shallow bay just south of the land, follow right up here, the path of the cyclone came at Mission Beach there, and 5.3 meters storm surge in Cardwell, and we managed to capture that pretty well in our simulations. And looking at wave setup, so this is the difference between a coupled and an uncoupled run. Wave setup on the order of half a meter, but slightly less, around 40 centimeters. Maximum in the region surrounding Cardwell where the largest waves were, and decreasing as you go towards the south, so Townsville somewhere down here. This transect here at Cardwell from offshore to onshore, so a slice of the model showing blue total water level, red being wave setup, and green being the significant wave height. So wherever the wave breaking occurred and wave heights reduced, you got an increase in the wave setup. So offshore around the Great Barrier Reef, and then near shore where the wave breaking occurred. And the wave setup was also very sensitive to local bathymetry. So if you weren't getting the local bathymetry right, you weren't going to get accurate predictions of the wave setup. An interesting thing we found was that the maximum wave setup timing did not necessarily coincide with the maximum storm surge or even the maximum significant wave height. So up to 4 hours there where the largest wave setup occurred prior to the arrival of the storm. And then just to note that any sort of a generalization might not work in a lot of places. So the angle of the waves is very important for the wave setup and shadowing and all kinds of processes. So timing is important. The percent contribution of wave setup to surge shown here. So on the y-axis, the percentage of wave setup or of surge that's attributable to the wave setup is from between around 15 to 35%, reduces as the storm arrives because of the large storm surge, and then goes a bit wacky after that. And that arrival of the storm is the dashed line. The wave setup to the wave height ratio in this case was on the order of kind of 6 to 10%. And again, before the waves arrive. So if the wave's at 10-meter depth, kind of 10% of that might be transferred into wave setup, which goes along somewhat with the theory. But again, it's very sensitive to the bathymetry. So if you have some bathymetric features you're not resolving, you're going to get that wrong. The second thing I really want to talk about in a little bit of detail is the importance of the wave-dependent wind stress. So one of the benefits of using a coupled wave surge model is that you can allow for the wind stress to vary with surface wave conditions. So like in that picture there, when the wind's very strong, the friction is very different in the presence of waves as without. And in general, there are many available parameterizations for surface wind friction available. Shown on the left is 3 different common ones: a large and pond, Smith, and Huang, which is a bit more recent. Generally, on the x-axis showing increasing wind speed, and then the surface drag coefficient, which increases as wind speeds increase up to a point, and then generally they give some value where they just level it off, so it doesn't increase forever. It at a certain wind speed, they'll level off the drag coefficient, and that's standard in storm surge models. But more realistic is probably that it tapers off at a certain wind speed and then reduces as the wind surface gets, or the sea surface gets very large waves and very intense winds. So we compared 2 of these. So Smith 1980 parameterization with the wave age parameterization, which accounts for the wave conditions. This here looks at the maximum wave setup difference. So the wave age, so the wave dependent wind stress minus the default where it's not dependent on waves, and the wave setup actually changed very little. So between the 2 runs, it's almost negligible difference there. But where you do have a very large difference is the total water level, which was significantly lower near the location of landfall using the wave age formulation. In areas of less intense winds, the sea level was slightly higher, but really around Cardwell, you had more than a meter reduction of water levels when you accounting for the wave-dependent wind stress. This was an interesting result. And this really highlights the need to consider the reliability of your wind forcing and how it combines with surface friction. Because in this case, the default surface drag caused the model to be right for the wrong reason.